Welcome to Science Pills. The day fossil fuels died. How the Stellarator finally cracked fusion.
Right. And it's a topic that really feels like science fiction bleeding into reality.
It really does. I mean, imagine you're walking up to an abandoned coal power plant in the year 2035.
Okay, picture that.
Yeah, so you look at it from the outside, and the scene is exactly what you'd expect from the end of an era, right? The towering concrete smokestacks are totally cold.
The rail yards are just empty.
Exactly. Miles of coal trains used to idle there, and now it's just nothing. It looks like a monument to a forgotten century.
But then you walk inside.
Right. You walk through these massive industrial doors and step onto the generator floor, and engineers aren't tearing the building down.
No, they're actually rewiring it.
Yeah, they're taking those massive existing transmission lines and wiring them into this brand new, incredibly compact, just wildly complex machine.
A machine that is quietly holding a 40 million degree artificial star inside it.
Which is just mind-blowing. And today we're looking at a stack of sources that prove this exact scenario isn't just a fantasy, it's an industrial reality that's unfolding, like right now.
It really is. We have this fascinating collection of technical documents for this deep dive today. We're looking at recent papers from the Journal of Plasma Physics, operational updates from the Max Planck Institute in Germany, testing data from UW-Madison.
Oh, and those highly aggressive deployment roadmaps from commercial startups, right? Like Proxima Fusion and Type 1 Energy.
Exactly, mostly dating from mid-2025 through early 2026. And I mean, the underlying narrative across all these documents it's profound.
It really is because, the long-standing joke in the scientific community has always been that commercial fusion energy is 30 years away.
And it always will be.
Right, the perpetual horizon.
Yeah.
But looking through these papers, it seems like between May 2025 and March 2026, that joke just quietly expired.
The timeline completely collapsed.
Yeah. And so the mission for our deep dive today, for you listening, is to really understand this paradigm-shattering shift that just happened. We're going to explore how this bizarrely shaped machine, called a Stellarator, didn't just crack the physics of fusion, but it actually sparked this massive global race.
A race to literally manufacture artificial stars and plug them directly into our existing grid.
Exactly. So where do we even begin with this?
Well, to truly grasp the magnitude of what these teams have accomplished, we kind of need to trace the entire causal chain. We have to start at the subatomic level.
Okay, so getting into the really tiny stuff first.
Right, just understanding the sheer violence of a plasma physics environment and how you could possibly contain it. Then we can move up to the engineering of the supermagnets and exotic materials.
And then ultimately we'll look at the macroeconomic strategy of rewriting the global and energy infrastructure, right?
Exactly. It's a journey from atoms to the global grid.
Okay, let's start with the physics then. Specifically in Greifswald, Germany. This is the home of the Wendelstein 7X Stellarator, or W7X, which is operated by the Max Planck Institute.
Right.
And I was looking at the photographs of this machine in the Institute's press materials, and I couldn't make sense of its geometry.
It's pretty wild to look at.
Yeah, it doesn't look like a standard generator or, a neat symmetrical reactor. It looks like a massive metallic domet that has been crushed and twisted.
It goes in on itself.
Yes, by some sort of alien intelligence or something. It is just aggressively asymmetrical.
It really is. I mean, it is widely considered one of the most complex single machines ever constructed by human hands.
Wow.
Yeah, the documentation notes that the W7X took 9 years to physically build, requiring over 1 million hours of highly specialized assembly.
1 million hours? That's insane.
But that chaotic, twisted shape isn't an accident. Every single millimeter of those warped coils was meticulously calculated.
Right. There's a reason for the madness.
Exactly. But to understand why it's shaped that way, and why it achieved such a massive breakthrough in May of 2025, we first have to understand what it's actually trying to hold inside.
Plasma, right. The fourth state of matter.
Precisely. So if you take a gas, in this case isotopes of hydrogen, and you heat it up to extreme temperatures, the electrons are literally stripped away from the atomic nuclei.
Okay, I'm tracking.
So what you're left with is this chaotic, turbulent, swirling soup of electrically charged particles.
Yeah.
That is a plasma.
Right.
And the goal is to get those hydrogen nuclei moving so incredibly fast that when they smash into each other, they actually overcome their natural magnetic repulsion.
Because normally they would bounce off each other, right?
Yeah.
Like two positive magnets.
Exactly. But if they're moving fast enough, they fuse together into helium, and that releases a massive amount of energy.
Okay. Which brings us to the ultimate scoreboard for fusion, because I saw this all over the sources. They repeatedly mention something called the Lawson criterion, or the triple product.
Yes, the triple product.
I gather this is basically the math equation that tells you if your artificial star is actually going to burn on its own. Like, how does that scoreboard work?
Yeah, so the Lawson criterion dictates the exact conditions required for a fusion plasma to become self-sustaining. We call that ignition.
Ignition, okay.
It basically means the fusion reactions are generating enough of their own internal heat to keep the surrounding plasma hot.
So you don't have to keep plugging it into the wall to keep it going.
Right, you don't have to keep pumping external power into the machine just to run it. So the way physicists measure how close a machine is to this ignition point is with this formula called the triple product.
And it has 3 variables, hence the triple.
Exactly, 3 distinct variables that you multiply together.
Okay, let's walk through those 3 variables so you, listening, have a really solid foundation for the rest of this deep dive.
Sure. So the first variable is plasma density. This is simply a measure of how tightly packed your hydrogen ions are inside the vacuum chamber.
Like a crowded room.
Yeah, exactly. If the particles are too spread out, they're just going to fly past each other without colliding. You need a really dense crowd of particles to ensure frequent collisions.
That makes intuitive sense. More targets, more crashes. What's the second variable?
The second is the ion temperature. And the numbers here are almost difficult to process. We're talking about heating this plasma to somewhere between 30 and 40 million degrees Celsius.
Wait, let me pause right there. 40 million degrees.
Yeah, 40 million.
Because the core of our actual sun is what, around 15 million degrees?
That's right.
Why on earth do we have to make our artificial star more than twice as hot as the real one? That seems backwards.
It does seem counterintuitive, but it's because we're missing the sun's greatest asset, which is gravity.
Oh, right.
The sun is so incredibly massive that its gravity creates immense, just crushing pressure at its core. And that pressure forces the hydrogen atoms together.
But we can't do that here on Earth?
No, we cannot replicate the gravitational mass of a star inside a laboratory in Germany. So, to compensate for our lack of gravitational pressure, we have to dramatically increase the thermal energy. We have to make the particles move so furiously fast that they slam into each other with enough kinetic force to fuse. So, heat is essentially our substitute for gravity.
That's incredible. Heat replacing gravity. Okay, so we have density, which is crowding them together. We have temperature, which is making them move fast enough to fuse. What is the third piece of the triple product?
The third piece is the energy confinement time.
Confinement time. Okay.
This is basically a measure of how perfectly your machine acts as a thermos. Because even if you have a dense 40 million degree plasma, it's completely useless if all that heat instantly leaks out into the cold walls of the reactor.
Right. It would just instantly cool down.
Exactly.
Yeah.
So confinement time measures how long you can trap that thermal energy inside the plasma before it dissipates.
I see. So you multiply the density times the extreme temperature times the confinement time, and if that final number, the triple product, crosses a certain threshold, the plasma ignites.
Yes.
And boom, you have a working power plant.
That is the goal. And that brings us to the historic milestone of May 22, 2025.
Okay, the big day. What happened?
So on that day, during an experimental campaign designated OP 2.3, the team operating the Wendelstein 7X Stellarator achieved a world record triple product for this specific class of machine.
Wow.
Yeah, the entire physics community watched as they pushed the density and the temperature to just unprecedented levels for a Stellarator. And they successfully maintained that high-performance state for 43 seconds.
Okay, now I have to play the skeptic here for a second.
Fair enough.
Because if I'm listening to this, I'm probably thinking 43 seconds. That sounds like a blip.
It does sound short.
Right. When I turn on my air conditioning or plug in my electric car, I expect the power plant on the other end of the grid to be running 24 hours a day, 365 days a year. Why is a 43-second plasma run triggering this massive commercial race?
That is the crucial question. And the answer requires looking at the history of how we've tried to build these machines. Because for the last 50 years, the fusion industry has been completely dominated by a different type of reactor called a tokamak.
Right, the tokamak. I've heard that term.
Yeah, tokamaks like the famous JT reactor in the UK, or the JT6EU in Japan. They have historically achieved very high triple products. They've reached the extreme temperatures and densities required.
Okay, so they work.
Well, they only ever achieved those high-performance numbers for a few fleeting seconds before the plasma became deeply unstable and the reaction just collapsed.
Oh, So the historical approach has basically yielded machines that act like sprinters. They can hit the top speed, but they instantly run out of breath.
A perfect analogy, yes. So what made the 43 seconds at W7X in May 2025 so revolutionary was that it proved the Stellarator architecture could actually match the extreme, high-pressure, high-efficiency performance of the world's best tokamaks.
But without collapsing.
Exactly, without succumbing to those sudden instabilities. It showed that the twisted magnetic cage holds firm.
Okay, so 43 seconds was just them proving the point.
Right, and to be clear, the 43-second duration wasn't a limit of the physics. It was simply the predetermined limit of that specific day's experimental hardware run.
Oh, really?
Yeah, we know the machine can run much longer, because the sources note that back in 2023, the same W7X Stellarator held a plasma for over 8 continuous minutes, releasing 1.3 gigajoules of energy.
Wait, 8 minutes?
Yes. They had already proved the Stellarator was a marathon runner. It could run steady state for long durations.
Oh, I see.
What the 2025 record added to the picture was proving it could run a marathon at a sprinter's pace. It proved it could hold the intense, extreme pressure plasma required for commercial power without the cage collapsing. It demonstrated that the physics of steady-state, high-performance fusion were fundamentally sound.
That is a massive distinction.
Yep.
So the Stellarator just essentially leapfrogged decades of tokamak research by solving the stability problem entirely.
Completely.
Which naturally leads me to wonder about the fundamental architecture of these machines. Because if the Stellarator is suddenly the clear winner for running a continuous power plant, why did the entire global scientific community spend the last half-century pouring billions of dollars into tokamaks?
It's a great question.
Like, what is the actual physical difference between these two designs?
Okay, well, it all comes down to how you generate the magnetic cage. Remember, the plasma is 40 million degrees. If that swirling cloud of ions physically touches the metal walls of the vacuum chamber, two things happen instantly.
Bad things, I assume.
Very bad. The wall begins to melt, and the plasma instantly cools down, which kills the fusion reaction.
Right.
So you have to levitate the plasma in the middle of the chamber using incredibly powerful magnetic fields. It's an invisible cage. The difference between a tokamak and a Stellarator is basically how they build that invisible cage.
Okay, let's break down the tokamak first. How does the traditional machine do it?
Well, a tokamak relies on symmetry. It has a beautiful, smooth, donut-shaped vacuum chamber, and that's surrounded by large circular magnetic coils. But those external coils only provide part of the magnetic cage.
It's just part of it.
Yeah. To get the necessary twist in the magnetic field to actually hold the particles, a tokamak relies on a neat trick. It uses a transformer to induce a massive electrical current directly through the plasma itself.
Whoa. So the plasma isn't just sitting there being held. The plasma is actively acting as a wire, conducting a massive current.
Correct. The plasma generates its own internal magnetic field, which interacts with the external coils to complete the cage.
But wait, didn't we just establish that plasma is a turbulent, boiling, chaotic soup of particles?
We did.
Relying on a chaotic fluid to maintain a perfect, steady electrical current seems incredibly precarious.
It is entirely precarious, and that is the fatal flaw of the tokamak for commercial power. Because the plasma is chaotic, that internal electrical current can suddenly kink, drift, or destabilize. Physicists call these events disruptions.
Disruptions? That doesn't sound good.
It's not. When a disruption happens, the plasma current collapses in a matter of milliseconds. The magnetic cage violently vanishes, all that thermal energy dumps into the reactor wall, and the machine shuts down.
So operating a tokamak is basically like driving a highly tuned sports car on a sheet of ice.
Yes.
You, the operator, have to constantly, actively micromanage the steering wheel. You're monitoring this chaotic feedback every millisecond, making tiny, panicked adjustments just to keep the car from spinning out and crashing into the wall.
That is an incredibly accurate visualization. It requires continuous active intervention to stave off an inevitable crash.
Right.
Let's look at the Stellarator.
Okay, how does the weirdly shaped one do it?
A Stellarator completely abandons the idea of running a current through the plasma. It relies 100% on powerful magnets located on the outside of the vacuum chamber.
Ah, so that explains the bizarre, twisted shape of the W7X.
Exactly. Because they aren't using the plasma to create the necessary twist in the magnetic field, they have to physically twist the external magnets themselves.
I see.
The complex 3D shape of the magnetic field is permanently, physically baked into the solid geometry of the coils.
So if the Tokamak is the sports car on ice where you have to constantly steer, the Stellarator is more like a roller coaster or a slot car track.
Right.
The physical rails of the track itself dictate exactly where the car goes. There's no steering required at all. You just hit the accelerator, and the physical design of the track keeps the car perfectly locked in, loop after loop.
That's exactly it. And because there is no internal plasma current constantly threatening to destabilize, the Stellarator is intrinsically naturally stable. It doesn't suffer from those violent disruptions.
That makes so much sense.
Yeah, and this is perfectly encapsulated by a quote in the sources from Dr. Lucio Milanese, the Chief Operating Officer of Proxima Fusion. He states, "Design, not control, is our strategy. Stellarators are harder to design, but easier to run."
Harder to design, easier to run. That is brilliant. You front load all the difficult work into the engineering of the machine so that the daily operation of the power plant is actually boring and predictable.
Exactly. You want a boring power plant.
Right. Which brings me back to my earlier confusion, though. If this slot car design is so obviously superior for a power plant that needs to run 24/7 without crashing, why did we wait until the 2020s to build commercial ones? Why didn't Lyman Spitzer or the early pioneers in the 1960s just build Stellarators from the start?
Well, they tried.
Oh, they did.
Yeah, but they quickly hit an insurmountable wall.
Eh,
Mathematics.
mathematics.
The calculations required to perfectly shape a 3D magnetic field so that particles bouncing around at 40 million degrees never drift out of the invisible cage. I mean, it involves incredibly dense nonlinear equations. It's a problem of optimization across billions of variables.
Wow.
In the 1970s, 1980s, and even the 1990s, human beings simply did not possess the computing power necessary to solve those equations. Tokamaks, because of their smooth 2D symmetrical design, could be calculated using slide rules and early mainframe computers.
Ah.
But the Stellarator could not.
Oh, this is fascinating. So the breakthrough of the Stellarator isn't purely a physics story, it's actually a software story.
It's entirely reliant on the computing revolution. The sources make it clear that the current explosion of Stellarator development is a direct result of cutting-edge computation, AI-assisted design, and massive machine learning algorithms.
That makes perfect sense.
We basically had to wait for supercomputers to evolve to the point where they could rapidly simulate millions of different twisted coil shapes, evaluate how the plasma would behave inside them, and incrementally optimize the geometry until they found the perfect cage.
So the physics theory was always there, but the digital tools to draw the blueprints just finally arrived.
Exactly. The blueprints were waiting for the computers.
So we finally have the blueprints. The supercomputers gave us the shape, and the W7X in Germany proved in May 2025 that the shape actually holds the plasma in the real world.
Right.
But holding a plasma in a lab is one thing. Generating enough raw power to light up a city is another. So how do we cross the chasm from a successful physics experiment to a high-output commercial reactor?
Well, to cross that chasm, we have to look at how power output scales in magnetic fusion. And it relies on a brutal, yet incredibly advantageous law of physics.
Okay, what's the law?
The fusion power generated by a reactor doesn't scale linearly with the strength of the magnetic cage. It scales to the fourth power of the magnetic field.
Wait, I want to make sure I'm fully grasping the implications of that. The power output is proportional to the magnetic field strength raised to the fourth power.
Yes.
What does that actually mean for the engineers trying to build these plants?
It means you have a massive multiplier effect at your disposal. If you can manage to increase the strength of your magnetic field just a little bit, your fusion power output skyrockets exponentially.
Oh, I see.
But the problem the engineers faced was that the Wendelstein 7X in Germany was built using an older generation of magnets called low-temperature superconductors, or LTS.
Let's briefly demystify superconductors for a second. Why use them at all? Why not just use giant copper wires to make electromagnets?
Because copper has electrical resistance. If you pump the massive amount of electricity required to generate these magnetic fields through normal copper coils, the resistance generates so much heat that the coils would literally melt themselves into slag.
That sounds counterproductive.
Very. Superconductors are special materials that, when cooled to extreme temperatures, often just a few degrees above absolute zero, they lose all electrical resistance.
Wow. Zero resistance.
The electricity flows perfectly, generating zero heat, allowing you to create incredibly strong magnetic fields continuously.
Got it. So W7X uses these low-temperature superconductors. How strong is the magnetic field they produce?
The LTS magnets on the W7X max out at a magnetic field strength of about 2.5 Tesla.
Okay.
And to give you some everyday context, The giant MRI machine at a hospital, which has a magnetic pull strong enough to rip a wrench out of your hand from across the room,
Hmm.
operates between 1.5 and 3 Tesla.
Okay, so 2.5 Tesla is a very strong field.
It is, but it's not strong enough to make a compact commercial power plant economically viable.
So how do the new commercial startups get past that 2.5 Tesla limit?
By utilizing a breakthrough material science discovery that has matured over the last decade, high-temperature superconducting magnets, or HTS.
HTS, okay.
These are often made from an exotic ceramic compound called REBCO, which stands for rare earth barium copper oxide. Instead of thick, rigid cables, this material is manufactured into thin, flat ribbons or tapes.
Interesting. Tapes.
Yeah, and when cooled, HTS tape can conduct immense amounts of current and generate vastly stronger magnetic fields than the old LTS cables.
How much stronger are we talking?
Well, according to their technical roadmaps, Proxima Fusion is designing their commercial stellarator, called Stellaris, to use modular HTS magnets that can generate a magnetic field up to 20 Tesla.
20 Tesla.
But even if we look at a more conservative near-term target for early commercial plants, say around 9 Tesla.
Actually, let me stop you there and do the math on that, because I really want to see this fourth power multiplier in action.
Sure, let's do it.
So if an older machine like W7X operates at 2.5 Tesla, and a new commercial machine uses HTS magnets to reach a conservative 9 Tesla, 9 divided by 2.5 is 3.6. So the magnetic field is 3.6 times stronger.
Right.
Now, if I take 3.6 and raise it to the fourth power, 3.6 times 3.6 times 3.6, that equals roughly 167.
Exactly.
Wait, are you saying that by making the magnet roughly 3.5 times stronger, the reactor generates almost 170 times more fusion power?
That is exactly what the scaling law dictates, a roughly 170-fold increase in power output.
That's insane.
And if you push closer to 15 or 20 Tesla, the math gets truly staggering. That is why HTS technology is the linchpin of the commercial fusion era. It allows you to take the proven, stable physics of the massive W7X, shrink the fatical size of the reactor down so it's cheaper and faster to build, and still multiply the power output by orders of magnitude.
That feels less like an engineering upgrade and more like unlocking a cheat code in the laws of physics.
It really does.
But it also sounds incredibly precarious from a manufacturing standpoint, like exotic ceramic tapes, rare earth materials, complex 3D coils. Where on earth do you buy thousands of miles of this highly specialized HTS tape?
You don't just buy it off a shelf. And this is exactly where the narrative in our sources shifts from theoretical physics into hard industrial reality. The bottleneck for fusion has officially moved from plasma stability to the supply chain.
Ah.
In February 2025, the American startup Type 1 Energy announced a major collaboration with Pine Island New Energy Partners, or PINEP. Their explicit mandate is to accelerate and mature the supply chain for these exact advanced materials.
So they're not even focused on the plasma at this point.
Exactly. They aren't focused on the plasma. They are focused on how to manufacture the magnets at scale.
It's the Henry Ford moment. It's not about inventing the car anymore. It's about building the assembly line.
Precisely. And in Europe, Proxima Fusion's roadmap explicitly outlines their plan to construct a dedicated magnet factory backed by private investors, which they project will create up to 1,000 highly skilled jobs.
Wow, 1,000 jobs just for magnets.
Yeah, they are actively pivoting their entire corporate structure to answer the question, how fast can we manufacture 1,000 of these twisted HTS magnets?
Okay, the ambition here is staggering, but I feel like I need to bring us back down to earth with a massive reality check.
Yeah, me.
Let's assume the supply chain works. We have our perfectly twisted HTS magnets. We have our stable 40 million degree plasma. The fusion reaction is humming along continuously. We still have a fundamental problem.
Which is?
We have an invisible magnetic cage holding a miniature star. But how does that actually turn my lights on? We don't run our laptops on plasma, we run them on electricity. How do we get the heat out of the cage to boil water and spin a turbine without the extreme heat simply melting the billion-dollar machine?
That is the single most daunting material science challenge remaining in the field. And to understand it, we have to look closely at the byproduct of the fusion reaction itself.
Okay, what comes out of it?
When deuterium and tritium fuse, they create a harmless helium nucleus, and they spit out a single, incredibly high-energy subatomic particle called a neutron.
A neutron, which, as the name implies, is electrically neutral. It has no charge.
Exactly. And because the neutron has no electrical charge, it is completely unaffected by the magnetic cage. The magnetic field only traps charged particles, like the plasma ions.
Oh.
So these high-energy neutrons, carrying roughly 80% of the energy from the fusion reaction, simply ignore the 20 Tesla magnetic field and fly straight out of the plasma at an appreciable fraction of the speed of light, smashing directly into the solid metal walls of the reactor.
Whoa. So the magnetic cage is perfectly holding the star, but the star is constantly firing a barrage of invisible high-speed bullets directly at the machinery.
A relentless barrage. And when those neutrons slam into the metal lattice of the reactor wall, two severe things happen.
Okay.
First, they transfer their kinetic energy as immense heat. Second, they cause severe microscopic damage to the metal structure, knocking atoms out of place and making the steel brittle over time.
That sounds like a nightmare for the engineers.
It is. To solve this, commercial fusion reactors will feature a highly advanced component called a blanket.
I am assuming the term blanket is a bit of an understatement for what this component actually does.
It is a massive understatement.
Hmm.
The blanket is a thick, complex, multi-layered physical barrier that completely surrounds the plasma core, sitting just outside the vacuum vessel, but inside the supercooled magnets.
Okay.
I like to think of the blanket as the ultimate industrial sponge and radiator combined. It has three distinct, critical jobs it must perform simultaneously.
Okay, let's look at the mechanics of the sponge.
Yep.
What is job number one?
Job number one is heat extraction. The blanket has to physically absorb the kinetic impact of those billions of high-speed neutrons, capture that thermal energy, and transfer it to a flowing coolant like water or pressurized helium.
Okay.
That hot coolant is then pumped out of the reactor to a heat exchanger, where it boils water to spin a steam turbine, generating the actual electricity for the grid.
Simple enough in concept. Capture the heat, boil water. What is job number two?
Job number two is radiation shielding. Remember those HTS magnets we just talked about?
The ones that have to be kept super cold.
Exactly. They have to be kept incredibly cold to maintain their superconductivity. If the fast neutrons pass through the blanket and hit the magnets, they will heat them up and destroy their superconducting properties, which would shut down the reactor.
Oh, wow.
So the blanket has to be thick enough and dense enough to stop every single neutron before it reaches the coils.
So it's absorbing heat and acting as a ballistic shield. What is the third job?
The third job is the most remarkable. The blanket must chemically manufacture its own fuel.
Wait, I need some clarification on that. Generating power while simultaneously manufacturing the exact fuel you are consuming sounds suspiciously like a perpetual motion machine. How is that possible?
It relies on nuclear chemistry. The specific fuel mixture most commercial reactors will use is a combination of two heavy forms of hydrogen, deuterium and tritium.
Okay.
Deuterium is incredibly abundant. We can easily extract it from common seawater. Tritium, however, is a massive problem. It is radioactive with a short half-life of about 12 years, meaning it decays very quickly. Therefore, it is virtually non-existent in nature.
Oh, so you can't just go mine tritium somewhere.
You cannot go mine tritium. The global supply is currently measured in kilograms, mostly harvested as a byproduct from old fission reactors. If we are going to build hundreds of commercial fusion plants, the plants themselves have to create the tritium they burn.
And the blanket does this. How?
The interior of the blanket is filled with lithium. When one of those high-speed neutrons escapes the plasma and crashes into a lithium atom inside the blanket, a nuclear reaction takes place that splits the lithium, producing helium and a brand new atom of tritium.
It's amazing.
And that freshly minted tritium is then immediately captured, extracted from the blanket, and pumped right back into the plasma core to keep the fusion fire burning. It is an exquisitely elegant, closed-loop fuel cycle.
That is genuinely incredible. It's consuming lithium to synthesize its own rare hydrogen fuel in real time, but engineering a physical structure that can survive constant neutron bombardment, efficiently extract heat without melting, and circulate liquid lithium to breed fuel. That sounds like a metallurgical nightmare.
It is, which perfectly contextualizes a major development from our sources. The U.S. Department of Energy recently awarded a massive $19 million grant, known as the FIRE Award, to the University of Wisconsin-Madison.
UW-Madison, right.
The project is led by Assistant Professor Ben Lindley, and their sole focus is solving this exact materials bottleneck.
Yeah, the UW-Madison documentation highlights their testing methodology, and the scale of it is just terrifying. They aren't just running computer simulations, they are using a specialized facility operated by a partner startup called Shine Technologies. It's called the Shine Flare Facility.
The Shine Flare facility is essentially a weaponized neutron cannon.
That sounds intense.
It produces 50 trillion fusion reactions every single second. This generates the highest steady-state neutron flux ever created, specifically for testing these materials. They
Wow.
place physical samples of candidate blanket materials into this facility and blast them with an unimaginable barrage of neutrons to see how long they survive before the atomic structure fundamentally fails.
So they are subjecting these materials to the exact hellish environment they will experience inside the commercial reactor. What kind of materials are they testing? What survives that?
One of the leading candidates they are evaluating is a substance called FLIBE. This is a highly specialized molten salt made from a mixture of lithium fluoride and beryllium fluoride.
Molten salt.
Yes, and because it is a liquid salt, it can circulate continuously. The lithium inside it breathes the tritium, while the liquid salt itself absorbs the heat and carries it away to the heat exchangers. They are also heavily testing a liquid metal alternative, a lead-lithium alloy.
And we can see from the corporate roadmaps that the startups have already begun placing their bets on these materials. The Proxima Fusion documents detail the design for their commercial Stellaris plant, and they've opted to use something called a WCLL blanket.
Yes, that stands for water-cooled lithium lead. So they're using the lead-lithium liquid metal to breathe the fuel and highly pressurized water running through pipes inside the blanket to extract the extreme heat. What is most impressive in their technical brief is their calculation for the tritium breeding ratio, or TBR. Proxima states their blanket will achieve TBR of 1.07.
Let's parse that number. I assume a ratio of exactly 1.0 means you're breaking even breeding exactly 1 atom of tritium for every 1 atom you burn. So 1.07 means you are in a surplus.
Precisely. For every 100 atoms of tritium the plasma consumes, the blanket manufactures 107 new ones.
Oh, that's smart.
That 7% surplus is critical. It accounts for any inefficiencies in extracting the gas, and it provides a stockpile that can be used to jumpstart the next fusion reactor they build. Achieving fuel self-sufficiency isn't just a bonus. It is the absolute non-negotiable prerequisite for this industry to exist.
So Proxima is banking on water-cooled lithium lead. What is the American startup Type 1 Energy focusing on in their material science division?
Type 1 is aggressively tackling the other major heat problem, the diverter. While the blanket absorbs the invisible neutrons flying out in all directions, the diverter is the physical exhaust pipe of the reactor.
Exhaust pipe.
Yeah, the magnetic cage isn't perfectly sealed. It is designed to intentionally leak at specific points so that the cooled ash of the fusion reaction, the helium, can be scraped out. The boundary layer, where this plasma exhaust actually touches the physical metal of the machine, is the diverter.
And I imagine the temperature at that physical intersection is catastrophic.
The heat fluxes hitting the diverter plates are comparable to the surface of the sun. It is a blowtorch of continuous plasma exhaust.
Unbelievable.
To solve this, Type 1 announced a major partnership in early 2026 with Oak Ridge National Laboratory and the University of Tennessee. They are building a dedicated high-heat flux facility to physically test these exhaust components.
Wait, how do you test a component against the heat of a 40 million degree plasma without actually having a working commercial fusion plant to plug it into?
You simulate the blowtorch. They use intense, highly focused electron beams to blast prototype plasma-facing components. They simulate a continuous thermal load of 10 megawatts per square meter. And to prevent the physical tungsten, or advanced alloys, from instantly vaporizing under that beam, Type 1 is testing advanced internal cooling systems that pump highly pressurized helium gas through microscopic channels just beneath the surface of the metal.
Okay, let's pull all these threads together because the sheer velocity of this engineering effort is stunning. The W7SX proved that the twisted Stellarator shape solves the physics of plasma stability.
Right.
The development of HTS tape solves the problem of generating a strong enough magnetic field to scale up the power.
Yes.
The University of Wisconsin and Oak Ridge are actively validating the lithium blankets and helium-cooled diverters to solve the heat and fuel problems. We are watching a scientific theory harden into an industrial product in real time.
Which logically leads us to the final and perhaps most economically consequential piece of the puzzle. Now that the commercial Stellarator is moving from the whiteboards to the assembly lines, the multi-billion-dollar question becomes, where exactly do we put them?
Right. Grid integration. You can't just drop a 350 megawatt fusion plant in the middle of a random field.
Definitely not.
Constructing a brand new power plant requires navigating decades of environmental reviews, securing massive water rights for cooling towers, negotiating complex local zoning permits, and, hardest of all, building hundreds of miles of new high-voltage transmission lines to connect the plant to the national grid. The regulatory friction alone could delay deployment by 20 years.
The fusion startups are acutely aware of this regulatory friction, and their strategy to bypass it is both economically brilliant and deeply symbolic. They aren't going to build in empty fields. They are actively targeting the exact physical sites of the energy infrastructure they intend to render obsolete.
Let's look closely at Type 1 Energy's deployment plan, which they have dubbed Project Infinity. This isn't just a speculative PR campaign. They have formed a concrete partnership with the Tennessee Valley Authority, the TVA, which is one of the largest utility providers in the United States, managing power for tens of millions of people.
Not a massive utility.
Type 1's roadmap aims to deploy their Infinity 2 pilot plant, a Stellarator generating 350 megawatts of electricity by the mid-2030s. And the location they have secured is the decommissioned Bull Run fossil fuel plant in Clinton, Tennessee.
A massive, retired coal-fired power plant.
Exactly. And this isn't an isolated, uniquely American strategy. If we look across the Atlantic at Proxima Fusion's European roadmap, they are following the exact same playbook. Proxima outlines a two-step deployment.
Yes, the Alpha and Stellaris projects.
Right. First, a massive €2 billion project called Alpha, which will be a demonstration stellarator built in Garching, aiming for scientific break engine, meaning it outputs more thermal energy than the facility consumes to run. But the next step is their commercial plant, Stellaris, and they have signed a memorandum of understanding with the Free State of Bavaria and the utility giant RWE to construct Stellaris at the site of the former Gundremmingen power plant.
And Gundremmingen isn't a coal plant. It is a massive, decommissioned, nuclear-fission power plant.
There is such a profound, almost poetic symmetry to this strategy. But strip away the poetry and look at the brutal pragmatism. By building your shiny, new, high-tech fusion reactor literally inside the shell of a dead coal or fission plant, you inherit an empire of existing infrastructure.
You inherit everything.
You are taking a workforce that has generations of experience managing high-pressure steam turbines, electrical switchyards, and industrial safety protocols, and you are retraining them to operate the clean energy grid of the future. It is literally the phoenix rising from the ashes of the fossil fuel era. The old grid is being replaced from the inside out.
It is a master stroke of deployment strategy. It shaves years, potentially decades, off the timeline by leveraging the incredibly hard infrastructure work that the fossil fuel industry already completed a century ago.
We have covered an immense amount of ground today. We started by staring at the chaotic, alien geometry of the W7X in Germany, watching it hold a 40 million degree plasma for 43 seconds. We unpacked the triple product and realized that those 43 seconds proved the Stellarator was the ultimate marathon runner of plasma physics.
We contrasted the white-knuckle, micromanaged steering of the Tokamak with the smooth, physics-baked rails of the Stellarator.
We saw how the rise of supercomputers finally unlocked the 3D math, and how twisting HTS tape into massive magnets multiplied the power output by a factor of 170. We dug deep into the extreme material science of liquid lithium blankets breeding their own tritium fuel and helium-cooled diverters surviving the heat of the sun. And finally, we saw how these artificial stars are going to be slotted directly into the rusty shells of our old coal plants.
The velocity of this narrative is truly breathtaking. In the span of just a few years, from the experimental proofs of May 2025 to the hardened industrial roadmaps of early 2026, we have witnessed fusion energy transition from an eternal physics experiment into a viable, rapidly scaling engineering reality.
And if you are listening to this right now, whether you're commuting to work or relaxing at home, I want to connect this massive technological shift directly back to your daily life, because this isn't just an abstract academic exercise happening in a laboratory.
Far from it.
The aggressive timelines laid out by these utilities mean that the electricity powering your home, charging your electric vehicle, running the servers that host your digital life in the late 2030s, it could very well be generated by a continuous artificial star sitting inside what used to be a dirty coal plant just down the highway. The day fossil fuels died isn't some arbitrary distant date in a sci-fi future. It's the day the Stellarator finally proved that human beings could simply design and build a fundamentally better fire.
As we close this out, I want to step back and offer one final overarching thought for you to mull over. It's a concept that wasn't explicitly spelled out in the physics papers or the engineering roadmaps, but it is the ultimate, inescapable implication of everything we have discussed today.
What's that?
For all of recorded human history, global power, immense wealth, and international geopolitics have been dictated almost entirely by geographic luck. The nations that wielded the most influence were simply the ones that happened to be located on top of the largest coal seams, the deepest oil reserves, or the richest natural gas deposits. We have fought countless wars, built empires, and held entire global economies hostage based purely on the terrestrial extraction of hydrocarbons.
The ultimate paradigm. If you have the oil, you dictate the terms of power.
Exactly. It is an economy of extraction. But if commercial fusion truly succeeds, if companies like Proxima Fusion and Type 1 Energy execute their roadmaps and mass-produce the Stellarator, energy is no longer an extracted resource tied to geographic luck.
Yep.
It becomes a manufactured technology. You can put a Stellarator anywhere on the planet. You don't need an oil field. You just need the intellectual capital, the AI optimization algorithms, and a robust supply chain for superconducting magnets and lithium. So if the ultimate source of global limitless power relies purely on who can best manufacture twisted coils and write machine learning software, rather than who happens to sit on a geological reserve, how will that permanently, fundamentally rewrite the geopolitical map of the world?
That is a profoundly staggering thought to end on. We are watching the transition from scraping dirt and burning it to manufacturing the machinery of the stars. Thank you for joining us on this deep dive into the documents. Keep your curiosity alive, keep looking for the underlying mechanisms of the world, and we'll catch you on the next deep dive.